maybe the vacuum is the lowest energy. All right, and if you have, the ground state of the electromagnetic field in the vacuum, all right, and then what frequencies could you have of the electromagnetic field in the ground state of the vacuum?
Any frequency?
Any frequency, in fact, all frequencies. So how much energy does each one of those frequencies have in its ground state? Half a chunk of energy, so half of h times, it's h times frequency over 2. But then how many frequencies?
All of them.
All frequent, infinite. So what is the energy of the vacuum with ground state electromagnetic fields in the ground state?
Still infinite.
Infinite.
Half of infinite is still infinite.
Right. So the vacuum, full of electromagnetic fields in its ground state, right, should have how much energy?
All of it.
An infinite amount of energy. All right? So this leads to a big problem. All right? Now, if you have it, what does energy do to space-time?
MC squared.
It distorts it.
It distorts it, right? Like mass?
Does it do? Yeah.
Okay, so forget about the air around me. Imagine taking away all the air so we have just a vacuum, right? And I try to look at my finger, right? But from between my eyes and my finger, through the vacuum, how many frequencies of the electromagnetic field are in there?
All of them.
All of them. How much energy does each one have in its ground state?
All of it.
H bar omega over 2 for every frequency. Therefore, the energy between my eyes and my finger should be infinite. And if I have an infinite amount of energy, what does energy do to space-time?
Warps it.
So should I ever be able to see my finger?
No.
No. All right, so do we have a contradiction?
Yeah, because you can clearly see your finger.
Yeah, I can kind of see my finger. So there's a big contradiction between experiment and theory for this whole thing. All right, and in fact, it's considered the biggest contradiction in theory and experiment in this whole game of quantum mechanics.
Is this right here?
Is this idea that I can see my finger. All right, and it's off by 120 orders of magnitude. So the calculations between how much energy there should be between my eyes and my finger and what is experimentally there. So it's something like the energy density should be like 110 to the 120. All right, whereas I don't see anything because I can see my finger. There's no warp into space-time. Right, and so that's a contradiction.
It's a big problem.
Okay, it's a huge problem. And so what might you say about this whole theory?
It's incomplete.
It's garbage. All right? Okay, now here's another thing, and this is what you've got to look up. All right? So this would be garbage, but there is an experiment that verifies this. And that's called the Casimir experiment.
Oh yeah, the Casimir.
The Casimir effect. Casimir.
Yeah.
All right? And let me and so what you need to do in addition to that other homework that I said do, all right, is you've got to do this for homework. Go find a recent article on the Casimir effect. And the ballpark idea of the Casimir effect goes like this. You take two plates, right? Two metal plates. And in between there's nothing. Right? But how many standing waves fit in the plate? So if we have a vacuum with every frequency, right? Every frequency is there. But if I put a plate right here, right, and I have boundary conditions on the plate, how many of those waves, can every single one of those waves now fit between those two plates? Okay, no. So there's more waves on the outside, ground state waves on the outside, than there are ground state waves on the inside. Alright, and so that should result in a pressure. And so what should happen to those two plates?
You should push together.
So in a vacuum, just putting two plates like this, they should feel a force that pushes them together. Everybody okay? Alright? from the calculations, doing this thing, figuring out the energy density of all the electromagnetic fields in the ground state with a half a quanta of energy for each frequency, you can calculate how much force that should be. And lo and behold, when you do the experiments, guess what happens?
You get that much force.
You get that much force. And these two plates press together by confining the vacuum energy density inside of here, and it feels the pressure on the outside. Matt, so have I answered your question? All right. But is this a big question that everybody
That means
has?
something else is letting you see your finger.
So
From that
something
point of
else
view.
is going on. So look this up. All right. So look this up, and maybe some of these articles have more insight into it.
So, like, this, what you're saying, it corresponds somehow to this whole idea of the Heisenberg uncertainty principle that you're going to have. That's kind of like relates to the Casimir effect, and from what I've read, is that it's the Heisenberg uncertainty principle. That is, you get the plates, the distance between those plates smaller and smaller. That delta x goes smaller and smaller, so the momentum has to increase.
Okay.
Something like that.
Yeah, so when we're talking about the momentum, right, you can write the momentum
Yeah.
as 2 pi is momentum equals h over wavelength,
Yeah.
right? And so the momentum is related to the wavelength. And so you can get this into the Heisenberg uncertainty principle for sure.
Yeah.
Well, yeah, that's h bar over 2, right?
Yeah. All right, so it's all related. All right, so where are we at? We're at this big, question that I don't have an answer to, and nobody does. All right?
I think if we can, I think the thing that will actually solve this would be if included somehow the force of gravity or something.
Look, it has to come in. I mean, gravity has to be reconciled with quantum mechanics.
I think that's what will actually solve the contradiction.
Yeah.
I was going to say that whole thing with gravity and all that. Yeah, I don't know explain it.
I mean, the problem here is like gravity is so weak, right? It's 10 to the minus 34 times weaker.
Yeah.
Now all of a sudden you've got it that if you have this energy density, and the energy density per unit centimeter is still going to be huge, then gravity is not small.
Yeah.
Right? So it's not the small effect in that little centimeter cube of space. Okay, so maybe it is negative. So this is what you guys have to look forward to. This is the
Like negative math.
These are the
That's
discoveries you guys got to make. All right?
Maybe the strophics. That's right.
Pretty wild, though, huh?
That infinite density of math.
Okay,
Binds
so
nucleons together.
I don't want to take us too far astray because what we're trying to concentrate is solving some problems, all right, in harmonic oscillators. I just want to point to these bigger questions that are there in physics and that you can go to graduate school. My friend at Yale is a leading expert on Casimir first. His name is Steve Lemerow. All right, and I can almost guarantee you that the articles you'll find will probably be written by Steve. I mean, he's the world's leading expert on the Casimir force.
So for homework, you wanted us to find a paper related
Find
to
the
it
paper, yeah, and read it.
and read it.
Actually read it.
What about the other thing you said there was a problem you said earlier? I wasn't here.
I forget.
I've got the,
I wasn't here either.
It's not going to be like 30 pages long like the last one.
Yeah, I wasn't here for that one, Jeremy. Okay. Here's the other thing I want to point out too. All systems, here's our nice model of the atom that Richard built and everything. And again, it's systems near stable equilibrium can be described as being in harmonic potential wells. And if you're in a harmonic potential well, you can therefore describe the forces as coming from springs. And therefore, it's no surprise that when we make models like this, we put springs between it, right? All right. What I want to draw your attention to is just to introduce a term, is that in a solid, when you compress things and let go, it vibrates, and it's obviously from a harmonic oscillator. Then what happens is you quantize the vibrations in the solid, and those are no longer called phonons, like we're thinking of phonon of energy, h bar omega, or h times frequency as a photon.
Photon.
All right. In a solid, those quantized lattice vibrations are called phonons. So in a solid, instead of like making a transition where you kick out a photon of h bar omega, in a solid, when you kick out, energy, it's in terms of a vibration, and that vibration is called a phonon, P-H-O-N-O-N.
For
You talk about that in experimental lecture.
Yep, so you need to know that. So in experimental and NMR, that's how things decay. So if you have a solid, you're more likely to decay you're more likely to relax. If you excited solid, you're more likely to relax as a solid and come back to your ground state by kicking out vibrations in the solid. And those vibrations are phonons, as opposed to relaxing by kicking out a photon. So in other words, I hit this, right? And you don't see a whole lot of light coming out, all right? But what's being spread about this thing are a lot of vibrations, and those are the phonons.
So what makes the difference between whether an atom will kick out a phonon or a photon? Is that just based on what is next to it, or what it's going to be around it?
It's related to all those things. And that's what your friend does. He's a solid state guy.
Yeah.
So if you do solid state physics, these are the questions you ask and you figure out. And they're huge, and you can see why it's related to industry. So in industry, people that do solid state, they make buildings that can withstand, nuclear reactors and, huge pressures and huge energies and different things. So the solid state physicists do this type of stuff. In general, like for me, like I do atomic physics and all this stuff, it's just an isolated atom that we're looking at. And so the relaxation is more because the photon is kicked out and not the phonon. So it's definitely a solid state type thing. All right?
Depending on which state it's in, if it's liquid.
All those are going to come in. And so it's solid state physics that do that type of thing. And they're great. They're the people that do superconductivity. They're the people that do semiconductors. They do solids, stuff like that. For a while, the hottest you could be as a physicist was definitely a solid state physicist, because it has direct ties to industry and a lot of different industries. Tons of different industries. Semiconductor industry, building industries. All right? So I certainly don't have a heck of a lot to say about that other than what I just did, okay? But it's really a very important thing. All right, now, the last thing that I want to do is, so we now have a prescription to solving the stationary states of the harmonic oscillator. All right, so way back to our original problem, the first thing you do is you find psi 0, right? How do you find psi 0? A dagger minus on psi 0 equals 0, 0. Okay? Once you find that, then you can find psi n of x's, they equal 1 over the square root of n factorial, A dagger plus to the n times psi 0. Everybody agree? Okay, and then how do I find this? Psi n of x and t, which are solutions to the time-dependent Schrödinger's equation. Oh, and let me say over here, En's equal, what did we say? H bar omega n plus a half? For the En's?
Yeah.
Okay. So, what are the psi n's? The capital psi's. Guys, you guys should all know this now. I stress this so that my head's going to explode.
Psi n of x times.
It's going to equal e to the I.
Okay.
And
E to the minus I, E n over h bar t, and
times
psi n of x, right? And I think that normalization is 1 over right there, 1 over n factorial.
Is that the right normalization? Because that's not reference.
It's not?
No, 189 Look at 2.59. Or 12.59, 346.
I'm using like 267. And then when normalization may get more complicated, but that's what he has here. Equation 267. I did not do the normalization. So I'm just using the result there. All right, now, let me say a couple things about these. Tell me something about these solutions.